Let's see. So, we were going to start something new today. We're going to start the newer brand of algorithms in RL, the policy gradient algorithms. In general, of course, that's the most obvious thing you would like to do. And as we'll see, there is, of course, it's the most natural thing. You are looking for a policy. In many cases, in many problems, it's harder to come up with a reward or a value function, especially when you're designing something. There are various things that you have to come up with. But thinking of a policy is more natural phenomena, right? I mean, simply, if you think of a robot moving or anything, it's more natural to think of whether I should put this hand here, put this here, put this there, or whether you should optimize how the values are and so on and so forth. So in some ways, policy optimization is actually the goal, and of course, is the natural idea. But any algorithm, for example, we'll see the gradient ones today, have a lot of variance to them, so they are harder to converge. Right? They're not so data efficient as you'd like. So we'll talk about sample complexity some point of time in the course, and this is one of the things that they're not so efficient with data, the policy-based algorithm. So they have their drawbacks. On the other hand, they're natural, and now people have, over the time, come up with fine refinements that help them being implemented. But we're talking about the framework today, and I will repeat some of these things again next time, because today I'm not going to do the mathematics, or not much of the mathematics, and probably not even next time, but we'll repeat this again because it's a little bit intense in some sense. So let's begin. So what are we looking for? Which one is this one? So what are we looking for? We're looking to find the best policy. Right? This is the goal, anyways, in reinforcement learning, to find the best policy. But the thing is, when you consider the policy optimization framework, we know already that there is a deterministic, at least in an MBP formulation, when you have a Markov decision process. Is it lecture 2 or something that we saw that there is a optimal deterministic policy, right? So you can say, oh, why not just work with deterministic policy and try to find an optimal deterministic policy, but it doesn't work like that in implementing the algorithm. And let me just briefly pause and give you an example. So suppose you have a state and you have action 1 that takes you to S1 and action 2 that takes you to S2. Okay, simple fact of life. So you choose a policy where you take the action 1 when you are, so you choose a deterministic policy. Why of when you are in this state, you take action 1, right? Whereas the other policy, so this is the policy 1, and the other policy, let's say, choose the action 2. Now, what does this mean? It means my graph is I get, so let's just represent this as 0 and 1, for example. So I get 0, 1 at this, and 0 at this. That's my first policy. The other policy is getting 1 at here and 0 at here. Right? And there is no way to change from one to the other. There is no way to change from one to the other in a smooth manner. What you want, if you want to be able to do something like a smooth operation, like a gradient descent, what you would want is something in between. You would want something as well, pi t as, which will give this the probability of, which will be t if for A, and 1 minus t for, A1 and for A2. So if you now make this policy, it varies continuously or smoothly in the parameter t, starting from this deterministic one to that deterministic one. So it varies now smoothly, and you can now think of applying something like a gradient descent to some such choice. Right? So this is something that's not often emphasized enough. Why you need stochastic policy. So this is, of course, now a stochastic policy. It doesn't say always choose A1 or always choose A2. It says choose A1 with probability T and choose A2 with probability 1 minus T. Right? This is what this policy is. It's a stochastic policy in between. So if you want to go, if this was not a right policy, how is something going to learn by gradient descent to go to there? It needs to have a smooth interpolation between them. So although it looks strange, but this is a necessary requirement that when we consider policy optimization, we start with this is basically why you need it. There are other good reasons for it. For example, if you are in some sort of a multi-agent or a game situation or an adversarial situation, then of course you cannot have a deterministic policy. You cannot play, even a 5-year-old knows that playing rock, paper, scissors with a constant policy will lose. Right? You have to have a random policy. So that's the other reason. In a multi-agent situation, it's pointless to. We saw this. We need Nash equilibriums which are not necessarily deterministic. Okay? That was in the last lecture. So that's another reason why we need stochastic policies. And of course, if you don't know all the features of your state, right? So if your knowledge of sometimes people call it partially observed ambiguity, but if your knowledge of what state you are in, which is usually incomplete, I actually don't know what state of my life is, right? There's so many factors, right, from war somewhere to prices of something, all that influence my life. A lot of things are invisible. So that is why you cannot be deterministic. In real world, you cannot be deterministic. So before we go in all the steps, we will assume our policies are stochastic. This is an important part of the deal. Actually, so now your goal is to find the best policy. And how does one find best of anything in mathematics? You do a optimization process. An optimization process works by choosing what one calls an objective function. What's an objective function? A function whose value you either want to maximize or minimize. Right? When you say something is best, what does it mean something is best? When I say a straight line is the shortest path from A to B, what do I have to do? I have to find all paths from A to B and compute the length of the path and then find the one that has the shortest length, right? Then the objective function in this problem would be the length of the path from A to B. So you assign to each path a length, and your job is to find the one that has the shortest length. So always in an optimization problem, you have this concept of what's called an objective function. I suppose most of you are familiar with it, but I just repeat it. Whenever you're looking for something best, your job is to define what best means first. And that what best means is given by objective function. So in principle, there are choices of objective functions. And one has to be very careful because if your environment is what one calls episodic, if there are terminal states and you will hit them in finite time, then you have to consider, or your goal is to hit a terminal step in finite time, like win a game or find the shortest distance or whatever. You have some sort of a terminal thing. Then you have to use something that takes the whole trajectory, the whole episode into mind. And so in these cases, a good objective function is the value function. Okay, so if you have MDP where you're looking for ending the game in an episodic way, your objective function should be something like the value function. So it's also important that we are not talking about the same objective function all the time, but it turns out, luckily, the mathematics is not very different for them. So, but still, one has to know which one we are using for what purposes. So this is one instance. What can be the other situation? If I say if I'm not in a terminal situation, what can be the other way of what other things MDPs can one be interested in? So something that is like real life, that doesn't terminate, that is just one whole sequence of things. So for example, if you want to train a robot to do something or to walk or whatever, there is not a terminal state. You just want it to improve every time it does something, right? Do it better. So in those things, you have other choices of objective functions. So usually, these are defined in terms of what is called the stationary distribution of a Markov chain. So before I either spend time explaining this or not, how many people know what a stationary distribution is of a Markov chain? Okay. So what one has, if I pick a policy, so let's go back to our theory for a minute, and I will explain this. So what I'm trying to do is explain this objective functions in the setting where you don't have an episodic problem, but which is a continuous problem, like a robot moving or any market moving or something like that. So in our MDP situation, what do we have? We have states. We have actions, we have some sort of a transition, reward, all that kind of thing. If you fix any policy, stochastic or non-stochastic, what does this do? It converts an MDP, so fix a policy, so it converts this MDP into a Markov process, essentially. Because now the actions are automatic. The actions are determined by your policy. So you, in every time step, you are in one state. Probabilistically, you took an action, and probabilistically, you will make a transition. Okay? So at every time, you move basically from state to state to state, and so on. So what you get whenever you have a fixed policy converts MDP into a Markov process. So you get a Markov chain. Okay, and of course, you want to consider some sort of a way of what happens if I put some mass on all my states. So my state space has some number of states, and as I go through this chain, my mass will move. So if I give this thing some probability, that thing some probability, as I go down in every step, the probability of being somewhere after a certain time changes. So I can start with some probability initially, but in every time, and in the limit, in the very limit, I could have a certain probability being in one state at infinity. After infinite iterations, I would have certain probability of it being in one state, certain probability being in the other state, and so on and so forth. That limit probability distribution is what's called the stationary distribution of a Markov chain. And there can be more than one. So it's the probability. So it's a probability mu. So a stationary. Oh, maybe I should use the other book. Or a Markov chain. So is a probability distribution mu, a probability distribution on state space. The stationary if mu equals p mu. So if I have this probability, and if I do the transitions and I redistribute the things, I get the same thing. This is what it means to be stationary. Usually you have one, but you can have more. But in this kind of finite thing, you'll get one stationary distribution. Okay, so this is what you have to remember about having fixed a policy. Always means that eventually you will have some probability of being in one state and some other probability of being in other states. Okay. So this will be something that I don't know. I'm not going to do too much mathematics today. I'm going to leave mathematics for the next time. But today's goal is to understand what the algorithm is and what the concepts are. Okay? And we'll do more detailed analysis. And of course, a different kind of approach next time. But let's just at least get our concepts clear. So again, if your process doesn't terminate, if you don't have terminal states in your MDP, then you're better off choosing other kind of reward, other kind of things to optimize. So what can you optimize? You can optimize that in each step you get the maximum return. So I don't know which one of the two is which formula. So one formula is to say, how can I guarantee that my policy provides me the maximum return in every step? And that's one possible, and there is an obvious formula for it, what it should be. If you understand the stationary distribution, that the formula for the J is then clear. And the other thing is, what if I want the maximum value in each step? Right? Average on average. Average get the best value. And that's the other kind of thing you could optimize. So if you don't have an episode, these are the things to optimize. But if you have an episode, don't try to optimize this. They will not provide. So if you choose this in the classic example is what's called the grid world. And it's very easy. I mean, so suppose you have a maze. You have a maze, and there is some. We talked about this kind of problems. So there is some place where you enter, and there is some place you exit. And your goal is to be as fast as out of the maze as possible. If that's your goal, you want this to terminate. And in this case, it's not good to think about getting the best reward in each step, because it might be that the best reward in each step is to just go back and forth here. And you never end up here. Right? So in such situation, you want to look at the whole episode when you want to terminate somewhere. Otherwise, you're just oscillating somewhere in order to get the best reward in the moment. Anyway, so that's just the comparison. So we have different choice of what does it mean to be the best policy. It is dictated by various things. So is that good? Okay. So of course, the first thing we want to do is the problem of optimization. So we could try to do a gradient. Well, since we are looking for the best policy, which in terms of our objective is going to be the maximum value of return, or maximum value of average return, or maximum value of the value function. So we are going to go upwards. So we are going to consider gradient ascent, right? So that's what this is. So you take this. So most of the talk today is about trying to do the gradient policy for one of these J's. So what is involved? I have a vague feeling that I forgot to say something, but I don't know what. We'll find out. Anyways, so what we want is to optimize this J using some sort of a gradient method. So for starters, what's a disadvantage of gradient method? What do you need, and what are the problems of using gradient methods? I think most of you are very familiar with gradient descent and so on, right? So you should be able to answer this question. What do you need? Yeah. Huh? Sorry? Gradient. You need a gradient. That's true. It might be hard to compute it, right? Yeah. Yeah. So, well, that is solved. We'll see a theorem that will compute the gradient of these functions. That will be in one of the slides. And the mathematics of that will be something that I want to cover next time a little bit more. But for now, today, we'll just see what the gradient is. A formula is there, and that can be learned. It's a formula that's learnable. The gradient is learnable in this situation. That's the good news. But you're right, that's one thing you need. How do you get the gradient? What's your assumption? That you have a smooth world. So we already took care of some bit of it. We said we will take stochastic probabilities, right? And like in this one-step example, where we chose this parameter t to represent our probabilities, this probabilities depend smoothly on my parameter t, right? In this example. And this is what you need. The second thing you need is that the policies, you have a maybe a neural network or linear representation, some function approximation of policies. So policies, of course, to be thought of as a function from your states to the probability space. Since this is all finite, this is a finite set, right? So it's a function between two things, and you want to make this maybe pi theta as a function from S cross something smooth, let's say Rn, any manifold if you like, doesn't matter. Okay, so you make it from something smooth into there, so that this dependence on this part is smooth. That is what you need to apply gradient methods, right? And it should be big enough. But what is also, it's actually written there. It's something that you cannot guarantee in gradients. You cannot. Sorry? Yeah, exactly.
Maximum.
Yeah, so we are looking for maximum in this case, but you can only find usually local optimas using gradients. And you will always, in this thing, you will end up in local maximums, not necessarily global maximums. Do you remember any ways of going around it? Huh? Sorry?
Different starting points.
Choose various starting points. So you guys, I'm just trying to revise your knowledge, if nothing else, right? So all these problems are implicit in what we are discussing today. All these problems are implicit in what we're discussing today, that we have to possibly run it with different initial points, and we have to be sure everything is smooth and so on. But assuming all that mathematics is well behaved for our problem, we can go on and consider gradient. So in any gradient descent or gradient ascent, what you need is to compute the gradient and move a step towards. Now, in this case, because it's gradient ascent, you don't have a minus sign. I think there is a formula saying you change your parameter by a small step size, alpha times the gradient, without the minus sign. Okay? This is how you change, because you're going to improve, you're going to maximize the function, right? And the most cheapest, simple-minded way of doing this is to actually take a finite difference, as an approximation of the derivative. So this you can more or less always achieve. So actually this is the zeroth algorithm, zeroth gradient descent algorithm. This is always what one should consider when one considers a gradient descent. Maybe you don't need to have the whole machinery. Maybe a simple-minded finite difference approximation to the gradient is good enough. And actually, I've seen various, I think there is a famous example is with this RoboCup robots, where they actually implement this kind of algorithm, simple-minded finite difference. So it's not something ridiculous, right? It's useful to remember, useful to know. Okay, so this is the thing. But now, as you said, the bigger trouble is what do we do with the gradient? How do we compute the gradient of these set of objectives that we want to maximize? What comes handy is this idea of a score function, which will. I mean, in this particular example, there is a very particular score function, and we will always think of this example and not other examples throughout our course, so we don't have to think about others. But score function is a what you call well-established mathematical concept about likelihood. You're familiar with this? Again, I sometimes feel I tell you things that you know. Okay. So what are we doing? We have a whole family of policies. What are policies? Policies are, in some ways, distributions valued in the space depending on some parameter space. Right? So this is your parameter space. At the end of the day, they are distributions in actions given these parameters S and theta. Okay. So now if I differentiate that with theta, the log of this distribution, the log of the likelihood function, so that is what one calls a score. Okay, and the score, we will also maybe next time do this calculation, but the score always has zero expectation. Well, always is nothing is always. One has to say if the dependence is good, like if you have this smooth dependence or whatever, then you can interchange some integral with some derivative or some summation can be interchanged. So convergences hold. So if that happens, the score has always zero expected value. So this is not just for this. If you have a map like this in any probability space in a parameter, you take the gradient, you call that thing a score, and that will have zero expectation. But we'll only consider our specific example with policies. Okay, so this is the score function for the policies, which is written up there. I don't want to write it again on the board, but actually, what is interesting and what I will probably not cover. So this is the mean. This is the expected value of this score. What is its variance? Its variance is what's called the Fisher information. Maybe we can think about doing this next time. The variance of score is what's called Fisher information. It's very useful quantity, and actually you can refine this gradient policy gradient algorithm quite nicely if you use the variance of this. Well, its variance is expected value of some function called the Fisher information, which is the Hessian of the log likelihood. So this is the score is this gradient of the log likelihood, and the Fisher information is the Hessian. So these are generally useful concepts in statistics. But we'll just use this for now because that helps us solve our problem. So, which is what you have in the next one, I think. Or did I put something else? Okay. I think this is. So I will not prove. I will give you this formula again in a minute. So I'll hide it, and I will give you why something like that you should expect to hold. But maybe next time I'll give you a proof. So in the slide that I have just switched off, there is a formula for what you wanted to know, right? So to do the gradient ascent theorem, we need to know what this is. Okay, and so there is a formula for this which is given by what's called the policy gradient theorem. This is basically a formula for this guy. Okay, nothing very hard. It's written up there, but I'm going to explain this at least heuristically today, maybe more rigorously next time. So suppose you have some, so usually there is, you consider a trajectory. So you start with some state S0, A0, R1, S1, R1. So you go around in the world as a robot, as an agent in your environment, and you learn that when you start and do some actions, you end up here. You get a trajectory. Okay, so what you want is something like your value function for this trajectory. Right? So what you get is V tau, if you like, is basically this. It depends whether you want to put gamma or not, but let me just put no gamma for the time being. It's just Ri. Just trying to do this. So this is for this trajectory. Okay, but how will you see this as a value function approximation? So if I was sampling these trajectories, what would I need to do is I would have to take the probability of my policy giving me this trajectory. There is a certain probability that I will get this trajectory with my policy times this maybe phi tau. Okay, so if I sum this over all possible trajectories, this should be kind of, well, this is part of a piece, right? So if I have this piece, I can extend it forever and make it into an episode. If I want to do the episodic calculation, if I can take something in between to do the average calculation. So this is a piece, crucial piece in our calculation. So it can be done to work in the episodic situation, or it can be shortened to work in the average situation. But this is the kind of piece that you're interested in. So let's just say this is, well, I should put a theta here. And I want to just find out what the gradient is. Right? So the gradient essentially becomes how these transition probabilities work here. So I would like to write so pi A S1, something like that. So I will get all these products because this probability is now a product of probabilities. Now a product of probabilities. What I'm doing. This probability is now a product of probabilities. And now suppose if I wanted to compute something like that, whenever you want to compute the gradient of a probability, you should actually know that what you can do is you multiply this by multiply and divide it by something like this. This is the stupidest trick in the book, and you should write this as okay. This is the whole point. But somehow now that I am having a product here in my formula, what happens is if I put a product inside something like that, so this whole thing is a product. If I put a product inside that, I would get a, let me just write it. So I'm trying to compute something like product of phi a as I plus 1, and this becomes heuristically the probability times gradient log of this product. I'm not writing the whole formula again because I'm just trying to explain what I mean. Plug this in here. Log of a product is sum. So you will get here some sum like pi log pi. Right? And this sum you can then rewrite as expectation of log pi. So this is the heuristic understanding of whenever you have to compute a sequence of things probabilistically, you would get a product of probabilities. A product of probabilities is hard to compute. So what you should convert is multiply and divide by this so that you can get a log object. In the log object, your product becomes a sum again. This is a common trick. You will see this hundreds of times. We'll do this for a particular calculation here. But I don't want to do it for just, well, I will do this maybe next time in detail for the particular calculation. But this is a common concept. Convert anything like this is a product of probabilities. You need a log to work with it. Okay? And it also then explains why I'm getting the formula that is written in this. So just 1 second. Let's start this again. Yeah, so this is the, or maybe there is a slight mistake in this. Let me check. Okay, I mean, okay, so there is a little bit of minor typo. Well, it's not a typo. I probably forgot to write something. There is no typo. Anyway, so the policy gradient theorem tells you what you were saying is hard to find, the gradient. Okay, so it tells you the gradient in a nice formula. It tells you the gradient in a nice formula, and the thing that I notice, so there are two different kinds of J's. So there is the J1, which is just basically the value function, and then there is the J average with V, and here you will have to use J equal to something like 1 over gamma times J average V. So you can use J equal to J1, but J equal to, you have to change it by a factor to get the same answer as is written. Okay, but it's a minor issue. But the policy gradient theorem, by the calculation, kind of calculation I showed, tells you that the gradient of any of these objective function is the expected value with your policy as a distribution, expected value of this thing. Right? So the funny thing or easy thing is that it immediately tells you how to learn this gradient, how to compute this gradient and use it in learning. Is we know how to estimate this thing. We learned this already in all our previous lectures. So if you want to do an unbiased estimate of this, what should you do? Monte Carlo. So just replace this by its Monte Carlo estimate. That will be an unbiased. And that just basically says, yes, you can learn the yes, you can learn the direction in which you have to move towards your local minimum. All right. So that's basically all about this theorem. So it's computationally not very hard, actually. That's also true. I want to have a bigger flavor for it, but it's computationally very easy. I want to cover the algorithms today, and we'll do some optimization mathematics next time. Okay, so this is what one would call sort of, what I had written before was what one would call a vanilla policy gradient method, as many people call it. Okay, but sorry, I'm already gone too far. Let me just wait for a second here. So if you think of this, you understand what the algorithm is, right? The algorithm is the grade, which I have not put in this slides. But what is the algorithm? The algorithm is, the goal is to find optimal policy relative to some j. So j is maybe say v pi. Let's just think of episodic to be concrete. So you want to find the policy that maximizes v, and your policies are, so your pi, theta are parameterized by some theta, right? So what you need is, you want to find at any step, you want to go to pi theta prime, so pi theta t plus 1. You need to find pi theta t plus 1, and theta t plus 1 is theta t plus delta theta t, which is alpha times delta theta j, which is theta t plus alpha times this quantity. Log pi sa dot gt. Gt is Monte Carlo approximation of Q pi. So this is how you change your update your policy parameter using a Monte Carlo approximation. Once you have updated your policy parameter, you are hopefully closer to at least your local minimum. Right, so this is the algorithm, just to be sure, which I think I forgot to write explicitly here. Okay, is this good? So this theorem, which computes your derivative, it has the name of a theorem. It has the privilege of being called a theorem because it's so useful. Okay, it's rather simple otherwise. All right. Close. Start that. So yeah, as I was saying, the main issue with any of these kind of approaches is what is the problem with Monte Carlo? Problem with Monte Carlo is variance. Now, when you put variance inside such a formula like a gradient descent, which itself has its own variance, then you get even a bigger variance. And your main problem becomes reducing the variance. So for the rest of the talk, we're just going to today we're just going to think about what are various ways of reducing the variance. And there are two main ideas in reducing the variance, and that's what I will cover today. Okay, so the first idea is what's called the actor-critic set of algorithms, and the second idea is what's called a baseline deduction. And baseline deduction is actually a very classical, old-fashioned way of reducing variance. There's nothing about it which comes only for policy or only for these kind of problems. This is a standard statistical tool to reduce variance. So MC plus gradient ascent high variance. Okay, and there are two strategies to get rid of it. One is what's called actor-critic methods, and two is baseline deduction. Okay, so this is the two things we'll cover. Before I cover actor-critic, just 1 second. Maybe I should just pause this for a second. The thing is that now we have a formula for sure for our So what we have, so one has to always remember this formula. So what we are updating it with is something like log phi theta. So this is the ideal formula, right? And what you want to approximate here is you want to represent this thing by some sort of a function approximation as well. Okay, so you have two function approximations. One function approximation is what's one called the actor function approximation, which is basically instead of pi theta is basically your parameterized policy. So there is someone who keeps track of them. So this depends on theta, and the gradient ascent method wants to compute the better value of theta. So you're only interested in changing theta as far as the actor is concerned. What does the actor do? It tries to do the gradient ascent to change theta so that you get a better pi theta. There are two kinds of parameters or two kinds of creatures in these algorithms. One creature is creature is a bad thing. Two kind of players, or I don't know. Huh? Two people cooperating in these algorithms. One guy is just sitting around and getting the next theta to update the policy. And the second guy is called critic. And what critic does is it takes some parameterized, so this is also what we learned in the function approximation lecture. So we can approximate the action state value using some parameterized function approximation. So there is someone who's trying to find the best approximation to this theta. So the Q depends on pi theta. So this guy gives me a pi theta. I use this pi theta to find Q pi theta, but as good as I can using a function approximation. Okay, so parameterized. Okay, so you have someone who is approximating the Q function, and once this person has approximated the Q function, you can use, the actor guy will go and change the pi theta to a new pi theta. Now this guy will now sit back and again approximate it. So let's write down a loop. So you start with pi theta, and the critic then produces Q, the best parameter for this. The actor produces pi theta prime. The critique produces Q pi theta prime as A. The actor produces pi theta next. So rather than saying theta prime, I should have T plus 1, T plus 1. So they are acting one after the other. So this, you start with the policy, the critic produces the value, the actor produces the new policy, the critic produces value, and so on. So this is a passing game between them, okay? So this is basically what an actor-critic method does. Right, so you need to, if you like, you can represent both of these things as neural networks. So one neural network that does the gradient ascent, not descent, but it's exactly the same neural network as gradient descent with a minus sign replaced by a plus sign. Okay, and so that one is called the actor. The actor is the gradient ascent neural network, and this is the neural network that we saw in the function approximation thing, or the linear or whatever approximation that produces the approximate value of the Q function. So you can consider this as a combination of, let's just say, two neural networks, for sake of saying it. All right, so let me see if I've forgotten to say something. Okay, so here I'm only writing how the actor updates its value. The actor updates the value of the policy parameter depending on what the critique has produced as Q. Right? So critique produces some Q, the actor updates the policy parameter. So you actually, this is like separation of jobs. There are two different jobs in any standard. You should have different classes and different functions to do different jobs. That's what it means. All right. So let's go on. So any questions about this? Oh, I should have let you think about it before I showed you the next slide. Ah, you saw it now. Let's say any questions about this. Do you think it will work? Just because I'm just proposing it, could it be that this does not work? Could it be that this will have issues? What can it have issues? Because this is the whole point. I mean, the recipes are good, but if you think about why it may work or why it may not work, you might come up for your problems better solutions. Right? So what can go wrong? What should be done? Why will this work? So in the next slide, there are the hypotheses under which it will work. As soon as I go to the next slide, you'll see the obvious reasons what you should make sure to guarantee this works. Okay? But we can think about it before we go there, because that's the whole point. So I have these things. What can go wrong? There are two things that can go wrong here, right? So one thing that can go wrong is I'm looking for this formula to represent the true what do you call it? The true update, right? The true estimate of the gradient. And one way to think about this is that as I am changing theta and w, I should have the same results regarding how my formula changes. Okay, so here is what are the two conditions. I mean, as soon as you see the conditions. Oh, did I go too far? Oh yeah, this is okay. So there are two conditions. If these two conditions satisfy, one is called the compatibility of the function approximations, and the other is that the Q approximation is actually very good. So unless your Q was not really producing the best result, the QW was not the best result, you can anyhow forget about getting good results for pi. And so the second condition is more or less obvious. The second condition says if you want good results for the policy, you better have good results for the Q value that you're putting in changing your policy. Second part is more or less obvious. The first part is slightly, but as soon as you see the proof, the first part will also become clear. So I will actually show you a proof of this. This is not so hard and more or less obvious. But if you have these two things, then the approximate computation that you do will be exact. It will produce exactly the gradient. Okay? You have to be sure. Whenever you have two things doing things, the combined work should produce the same answer as you expect. It's not going astray. Okay, good. And oh, I don't think I made a slide for that. That would have been nicer to have just written this down on a slide. Anyways, so I will write it down on the board. Oh, it's hard to remember when you remove these things from the slides, right? Now, I don't remember exactly the condition because memory is short. We use a lot of it for other purposes. Okay. Oh, this was clean anyhow. So I think I have what I've written there are two conditions. The first condition is that the gradient of my Q is equal to the gradient of So the way I'm changing my Q is the way I'm changing my theta. at least the score function. Right? You shouldn't change this different from the score function. There's one condition, and the second condition is that if I look at the approximation in this world, it's in least squares minimizing. So this is minimum. Okay, so there are two. The error is minimum, the least square terms, and the gradients, the change of this quantity with W. So this quantity W keeps changing as your policy keeps changing. We change policy, you change W. You change W, you change policy. Right? This is the whole point. When I change this, I will change up the policy. When I change policy, I will change the W. But how they are being changed has to be synchronized. Otherwise, you cannot expect the right answer. And this one is more or less obvious. You don't want me to explain that anymore. Okay? And the thing is that if this is a minimum, if this was minimum, then that means that, so this is minimum in W actually, right? That's what it means. W is chosen so that the parameter W is always such that this is minimum. And if it is such that it's always minimum in W, that just basically means if I take the gradient of this error, gradient of whatever e pi naught of this whole thing, square Q W. Somehow I get confused always. People write one subscript and one overscript, and for good reasons. This should be 0. If this is the best W parameter that does that for pi theta naught, then this should be 0. I can put this inside the integral. This anyhow does not matter my variable. And when I differentiate something that has a square in it, I get e pi naught of this thing. Maybe I should keep a half somewhere. I forgot about that, but that is it. Times gradient of Q. Okay, so this is just putting this inside. I'm keeping a half somewhere for the timing, forget about that. But now my assumption is this changes the same way as, in a synchronous way as that changes. Right? So if that is the case, then I can write this as right? But if you look at this quantity, this is your true, the expected value of this thing is your true gradient by the gradient policy theorem. So this width is with the expected value, the E of that is, and that quantity is what you're trying to say is the approximate. I say log gradient theta log ISA equals that. So I'm just taking this term out of the and integrating it separately. I will get that, or summing it separately, I'll get that. And that is the rest of the term that's remaining. So this is the one that you are trying to approximate, that becomes the true one. The approximation is the true one because you have synchronized the way W changes and theta changes, and because you've chosen W to be the best possible W. Okay. So one should not expect when one does some sort of an actor-critic method, two parallel ways of parameterization to work unless there is some synchronization between them. Okay, so there is some inherent need for that. But in practice, people try to fiddle with it till something works out. But in theory, this is when it will work out. Okay? Any questions? All right. So, okay, so maybe this is the, oh, sorry, it's not switched on. I'm getting a little too confused today in this room. I was doing some teaching in another room, and now I feel I'm in the other room. So the other way to deal with variance is the baseline, and this is a standard technique. This doesn't just come from here. It is standard. You should remember this word. If you think variance is one of your problems, you should think of the word baseline. Okay, so let's look at the formula again. Anyways, I will show the slide again, but the idea is that you're trying to update your policy depending on some Q function, some Q value, right? And suppose you're playing some game, you're playing chess, right? So if you win, you'll get a Q value of 1. If you lose, you'll get a Q value of 0, right? So when you lose, this whole change will have Q equal to 0. And will it do anything to update your policy? No. If you win, it will update your policy. But if you lose, it will not update your policy. So the whole thing is that you're not learning anything by losing, which is just terrible. You're only learning by winning. Although the formula is perfectly correct, the convergence will be very slow, and this creates the whole variance problem. So what you should do is use the fact that I think I had mentioned before, is that in the formula for the gradient, there is the score function, and its expectation is 0. Okay, so we can check this now. I will do this computation here on the board for a second, or you can do it yourself. It's rather simple. The score function is 0, so what you can do is multiply that score function by any function that does not depend on theta. For example, a function of the base of the state space. It should not depend on theta. That's all you on pi and pi theta. You can take a function of the states, multiply it. Its expectation will still be 0 in terms of pi theta. So you can subtract that from the whole thing, and you can. This is basically saying, well, maybe I should walk up here and say what I'm. Is there a formula not written here anywhere? Okay, here is the formula, right? So suppose you were playing the game as before, as I was saying, and Q was always 0 when you lose and 1 when you win, so it was not changing anything before. Now you say you subtract half here, not even depending on state, just subtract half here, the average of 0 and 1. So when you lose, you will learn something, because you're saying, oh, this is a minus number now, you should go in certain direction. When you win, you learn something, because there's a positive number, it goes somewhere. Only when you draw, when you really are on half, that you will not learn anything. Okay? So this adding of a term like this is mathematically justified, because this expectation does not change when you add this term. That is why it's called baseline. It does not change the expectation. It does not change your objective. but it reduces the variance in this very critical sense, in the sense that now you're learning every time you get an answer. So basically, what this number should be, it should be the average at S, what you should expect from pi. So the average, if you're doing better than average, those actions you should support. And the action that does better than average at S, you should make it less valuable. This is the whole heuristic about it. So if your action does better, then whatever you average at state S is, then you're fine. So what should be the average at state S? What's a good choice for average at state S? Sorry?
Average of all V1?
Sorry, I couldn't hear you.
Average of all the V1?
Or average on reward, or long-term rewards. So say your value function of S, something like that. Something that says, if I have this policy, if I have my policy, on average, I can get something on reward that's one thing, or what I expect to get is the same thing. What I expect to get as a reward is the value function, which is what you can plug in here, right? And once you plug that in here, you know that if your action does better than the expected reward from the policy, that action is towards improvement of the policy. If your action does worse than what the value function gives, that action is bad for, it should be discarded. So that should not contribute more towards policy. So, but this is not the only one. So there are many choices here, and they all work, or many of them work. So this is the basic outline of that. So maybe I'll see that. Okay, so I have tried to I don't remember. Is this the? Oh, maybe I should wait. This has too much information. I remember this. I only made one slide for what should be 4 slides. I'll have to talk a little bit about. So maybe I will just talk a little bit about what we have done with the baseline before. Oh, this is now a function error. Can you read this? Or I suppose yes. So the thing is that whenever you are having some so this is your formula, right? This is so first let's just understand why there is so much why there is so much variance in this formula. Why is there so much variance? Is you're kind of averaging. So this is an expectation. So you're taking the sum, you're taking averaging, you're taking an integration of this quantity. So this averaging means there can be a lot of, since you're sampling this depends a lot on how your sample is produced. What number you get depends a lot on what samples you produce. So it's very dependent how you produce this kind of sample. Okay, so what one wants is, of course, keep the same average. Keep the same average. Keep the same average. Why do we keep the same average? I did not do this in the last slide, but I should have. But we keep the same average because so if you just took if you did not have this Q term, this thing would have an expected value of 0. So anything that does not depend on pi theta, if I multiply that and take the expected value, that will be 0. So this is a very simple fact about all score functions, not just about this score function, but any score function. This is why that thing is 0. And so we can change this thing. And what you want by changing this thing here is now you want to learn better when you change when you get some. How do you change theta when you have different base things? So the standard idea is to replace this thing by the value function. So I'll just write it here. Standard idea is just take the value function of this. So what's happening if you change this? It means if action A performs better than the policy, if the action A performs better than the policy, you will have a positive input to your gradient. So you'll increase in that. That will contribute positively to your gradient. If the action A does worse than your value function, then it will have a negative contribution to your gradient. What do you want? You want to improve your policy. Right? So this is the whole point. So the thing is that this quantity, you call this quantity, the real one is this thing is called an advantage function. Okay, so it says how much advantage you will have if you had used the action A. That advantage can be negative. You might not gain anything if you use the advantage action A instead as, but you might gain something by using action A instead as. So this is the advantage function. Okay, and what you want is just a representation of this. So you can now make it. You can represent both of these things now by two parameters. So QW as A and V. So you can now represent both of these things by some function approximation, depending on two parameters, again, you will have to be sure that the parameters are somewhat synchronized to each other. And that will be some way to estimate the advantage function. Okay. So this is oh, I forgot to say something. So why does this reduce? Oh, I haven't. So heuristically, it's clear why it reduces variance, but actually the mathematics is not so simple as far as I see. And this is why I want to spend some time, maybe, how much time is it? Oh, we don't have, oh, man. Okay, then maybe I'll just, I did not realize we had so much time, like 5 minutes back when I checked. And now we don't. Then I will not explain the math today. It's just not going to work out, which is what I was trying to do. So anyway, well, then I will just explain what the algorithm is. The algorithm is rather straightforward, right? So you replace, to reduce your variance, you replace where you had Q before, you replace it by AW. By this advantage function, and you estimate it in either by one parameters or by two parameters. Both is fine. Okay, so if you want to estimate it with two parameters, you have to make sure that these two are synchronized. Or you can estimate it with just one parameter, where you can use the same thing to compute the value at the next action state minus the value at the state, and that will be your way of approximating the Q function just with one parameter. And in the gradient update, you could use this value instead of the value of the Q function. Okay. But now there is a bias in this, because this is not an unbiased estimate of the Q, but it has a lower variance. So it's again always the same thing, that you're coming back to saying TD has bias but no variance, and the Monte Carlo has variance but no bias. And this is apparently preferred in all applications. So there is some math behind all of this, and maybe other optimization math, and that is what we can do next time. And then the term after, or maybe in 2 lectures, we'll do the more advanced versions of this policy gradient algorithms. So maybe that's it for today. Let's stop here. All right. Any questions? Is this confusing a little bit, or a lot? I will
Take some time, I guess.
take some time to digest.
Yeah.
So is it a good idea to repeat some of this again?
Yeah.
Yeah, because I think, because I think if you're familiar with these concepts, like most people, when they do this, if you know the score function and why the expected value of the score function is 0, you immediately see that, of course, this is what you would do, right? But if you have not seen these things before, it's your first time seeing such ideas, then it's baffling. Why would anyone put a log there, right? Why wouldn't you not? Because of course, computing products is harder than computing some studies in any sense. So this becomes very simple if you revise some mathematics about this. But I also wanted to tell you beforehand that there is an algorithm which uses this, rather than just start, okay, let's today do some score function and Fisher information and blah, blah, blah. then it sounds more blah, 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 right? This way you know that this algorithm will need it. That's what we can do next time. Okay? And then we can revise this algorithms one more time. All right, so for today, I think we can stop. All right, let's just